In this particular lecture, we'll be discussing about feed-forward control. And as always, we will be discussing the theory portion first, and then we will be taking a practical industrial example with which I will explain you how the feed-forward control is working. And lastly, we'll be having a comparison between the feed-forward control and feedback control, and what are the advantages and disadvantages of the feed-forward control over the feedback control system. So traditionally, if we see, we mostly use the feedback control system. So what happens in the feedback control system? So feedback control system basically the manipulated variable goes to the process. So this is, suppose this is your process, and out of the process, then this process input goes to your controller, right? So, and again, this gets outputted here, okay? So, what basically happens is the controller takes this process variable, and based on the set point given on the controller, it generates the manipulated variable or MV, and this MV goes into the process, and then it tries to change the process, and then PB again changes. So the aim is to take PB close to the set point. So after some time, if the controller is properly tuned, the PB should reach your set point, right? And that time and this should go on, like what the response will be, like if there is a change in the set point, so initially there may be some shoot up, then slowly, if it is properly tuned, the PV will be slowly tracking the SP, right? So this normally happens in the feedback control system. Now, there are something additional that is always providing disturbances, right? So there are disturbances that is coming to the process. And that's why even you are in the steady state, so that time if disturbances comes, then again changes PV, and then it changes your manipulated variable, and process gets manipulated every time, right? So, so in this case, how the controller knows that there is a disturbance? It is basically through the change of the PV, right? So disturbance indirectly changes the PV. Now, this relation between the disturbance and PV may take a longer duration to take place, right? So suppose there is some disturbances, and maybe after 5 minutes, 10 minutes, or sometime maybe 1 hour, after that this PV gets changed. And when the PV gets changed, then only this controller, this feedback controller, takes some action and recalibrate the process, right? So that's why if there is a sudden or large disturbances that happens into the process, then feedback control is not quite effective. And sometimes it is like it disturbs the whole system. So what was thought was basically to have a different kind of control system where you have the process just like before, and this is the two things happening here, and this is the disturbances, right? Now, these disturbances, if it can be measured, right, and fed into the controller, and then controller taking action before even it changes the process variable, right? So in this case, this is the input, right? This is the input to the controller. This disturbance is the input to the controller, this is the manipulated variable, and this is the control output. Okay, so this is the way uh, feed forward. So this is known as a feed forward. So this is the way the feed forward control is normally configured. So hope you have understood this. If you have not understood, there's no issue. We have one practical industrial example coming up where this thing will be much more clearer to you. So let's go to the example. So in this case, we will be talking about feed-forward control of a heat exchanger. So there is a process fluid and it is getting heated in a shell and tube heat exchanger. And at the outlet of the heat exchanger, there is a temperature transmitter, and this temperature transmitter sends signal to a temperature controller. Right. So the process fluid is basically heated by a controlled steam flow. Now steam flow is measured by FT, and FT sends the signal to a flow controller, and this flow controller controls the control valve at the inlet of the heat exchanger, and thus the controlling the steam flow into the heat exchanger. And this way it controls the temperature at the outlet of the heat exchanger. Now we have already thought about the cascade control. So here our primary thing that we want to control is the temperature of the process fluid at the outlet of the heat exchanger, right? So temperature is our primary controller and flow is our secondary controller. So output of the temperature controller basically goes into flow controller as a set point. So as far as we know, and this is our basically our cascade control system, right? Now the problem is your cascade control system is working fine. Now if your process fluid itself, there is a change in the process fluid temperature or the pressure at the inlet of the heat exchanger, and that is very drastic, then this control system will be knowing that only through this change in the temperature, right? So suppose the process fluid was initially coming at 300 degrees centigrade. Now suddenly it has started coming at 350 degrees centigrade. When it was 300 degrees centigrade and our set point may be at 305 degrees centigrade and everything was stable, the valve was open, suppose 30%. This particular steam valve was open at 30% opening. Now the temperature has suddenly increased to 350 degree. Okay, so 350 degree, it is going through the same amount of the steam. It will increase the temperature here, but not at the time when the, so if we have a temperature transmitter here, so when it is 350 to reach this TT101, also 350 takes time because ultimately heat equilibrium have to be reached. So maybe after 20 or 30 minutes it will reach 350. Okay, or basically more than 350 because it is 350, it is coming entering, so it may be going like 370 or something. Okay, 370 degrees centigrade. So this change take time, and so when it is 370, then again you have to take action. Then the steam valve will opening will be reduced, and this way it will work. So in this process, what will happen is your already your process steam is coming in high temperature, you are overheating it. So you are wasting your steam. So your steam could have been saved. So this is one point. This is like saving or energy or optimizing your There are other things. In the downstream of this heat exchanger, it may go into a reactor for some reaction. And for that reactor providing a, a on-spec product, the temperature of process fluid is very important. So instead of 305 degrees centigrade, if 370 degree material goes into it, it completely disturbs the process, produces off-spec product, right? So which is not desirable again. Third thing, the temperature, if increase of the temperature in the process fluid at the inlet of the heat exchanger is very high, then it may dis it may cause a safety hazard because these pipelines and everything may have been designed for a certain temperature. So if it goes increases, it may lose integrity, right? The mechanical integrity can be uh, compromised. So that is one another thing. So to avoid all these things, we can do one thing, and that is to incorporate a summation block or additional calculation block between this temperature controller and this flow controller. And this will take input from the temperature and flow at the inlet of the heat exchanger, and it will go through a feed-forward calculation and feed into our summation block. Right? So now what happened? You know the flow and temperature, and if there is a change beyond your permissible range, this feed-forward controller will generate some additional bias into this temperature controller, right? So so it will add something into the temperature controller output, right? So suppose if your temperature, this feed forward calculation block sees that your temperature have increased, then it will incorporate some negative component into it, right? So so that what will happen, that this flow controller will now know that we have to decrease the temperature. So in order to decrease the temperature, it will reduce the steam flow to 28% or something. Due to reduced steam flow, the the process fluid will not get heated, right? And as a result, the temperature at the outlet is more likely to be at the set point or close to the set point. So this way, by introducing the feed forward mechanism, we are gaining we are gaining financially, we are gaining safety wise. Yes. So both side we are having savings. So if you see what are the advantages of the feed forward control, so it acts before the effect of the disturbance is felt by the system, and it is good for slow system or systems with dead time, because if the system is very fast to react with the disturbances, then it is of no use, because the PV will automatically change and the feedback control is there to take care of that. So it is not good for a very fast system. It is good for slow system. So slow system means like this temperature control. So it is good for the temperature control. It can be good for the pressure also to some extent. But if you want to control like flow, so flow is already very fast thing, and it will automatically change your PV, so it is not good for flow control system. Another thing, it does not introduces any other instability to the loop response because it is not directly making any loop gain or something. It is not increasing the loop gain or decreasing the loop gain. It is independent of that. It is just adding input. It is or adding or subtracting to your controller output, right? To act it most faster towards your set point. So hope you have understood about the feed forward control. If you have any doubt, please write in the comment box.